So we know we want to simulate the birthday problem in a computer. And that's all well and good, but how do we actually do that? How do we deal with something as complex as people and the day they were born and turn all that into a computer simulation? The way to deal with all this complexity is to distill the problem down into only the aspects of the problem we're interested in. Namely, we need to represent the problem in a way that allows us to solve the problem without representing anything we don't absolutely need. Let's set aside the birthday problem for a second and think about how we can solve other problems through simulation. For example, how could we simulate rolling a 6-sided dice in a computer? Because there are 6 different outcomes we're interested in, all we really need to do to represent the dice is to use 6 different numbers, like the numbers 1 to 6. We could simulate rolling the dice by randomly selecting one of the numbers from 1 to 6 with equal chances. To simulate rolling more than one dice, we could repeat this process many times. If we are interested in determining how often we could expect to roll a 2 in the long run, we could repeat this procedure many times and count how many 2s we observe. This would give us an estimate of the probability of rolling a 2 on a single dice. The more trials we run in our simulation, the better our estimate would be. Here's another example. How could we simulate randomly selecting a card from a standard deck of cards? This is a more complicated problem than the dice, because a deck of cards has 2 things we're interested in: the rank of the cards, such as 2, 7, or king, and the suit of the cards, such as heart or spade. But as long as we are only interested in differentiating the cards chosen, we can represent the deck of cards in much the same way as we represented the dice. We can use the numbers 1 to 52, because there are 52 unique cards in a standard deck. As with the dice, this gives us a unique identifier in our representation scheme for each of the things we're interested in. The number 1 would represent the ace of spades, 2 would represent the 2 of spades, and so on. If we were only interested in the rank of the cards and wanted to ignore the suits, we could represent the values of the 13 different cards with the numbers 1 to 13. Conversely, if we were only interested in the 4 suits of the cards and wanted to ignore the ranks, we could represent the suits with the numbers 1 to 4. In these examples, we've distilled the problem into only its essential elements and represented the problem in the simplest way possible. Now let's go back to the birthday problem. We're interested in representing each of the 365 different possible birthdays. The simplest way to do this is to represent each day of the calendar year with the numbers 1 to 365. We'll just ignore leap years. The number 1 would represent January 1st, 2 would represent January 2nd, and so on. We can then randomly sample a number from 1 to 365 to simulate randomly picking a person whose birthday corresponds to the number from 1 to 365 that we selected. To simulate the chances of 2 people in 20 sharing a birthday, we can randomly sample 20 numbers from 1 to 365 and see if any of the 2 numbers match. If there is a match, that represents 2 people in our group of 20 having the same birthday. If there is no match, then each of the 20 people have a different birthday. We can repeat this procedure many times and calculate how many times there are matches relative to how many times we repeated this whole procedure. This gives us an estimate of the solution to the birthday problem. Again, the more trials we run in our simulation, the more accurate our estimate of the solution will be. Let's apply this reasoning to see how we can build the heart of our computer simulation.